The appeal of a string counts how many distinct lowercase letters it contains. Given S, add up the appeal of every contiguous substring and return that total. Length 1, each single letter is its own substring with appeal 1. 5 singles give 5. Length 2, AB has 2 distinct letters, BB has 1, BC has 2, CA has 2. Those 4 add 7. Length 3, ABB has 2, BBC has 2, BCA has 3 distinct letters. 7 more. Length 4, ABBC and BBCA each contain A, B, and C, so 3 each. 6 total. Length 5, the whole string has 3 distinct letters, appeal 3. Add the buckets, 5 plus 7 plus 7 plus 6 plus 3 equals 28. Finding the total appeal of all substrings looks simple on paper. But for a string with 100,000 characters, the total number of substrings explodes into billions. Generating and analyzing every single one individually is impossible. We need a way to accumulate our answer incrementally. Let's simplify our mental layout by grouping substrings based on their ending positions. If we already know the total appeal scores for all substrings ending at our current position, how does introducing the very next character change those scores? First, consider a character we haven't seen in a while, or ever. When this new character is glued to the end of all existing substrings, it introduces a brand new, unique element to each of them. This means the appeal score of every single existing substring increases by exactly 1, plus an extra 1 for the new standalone character. This means our cumulative score moves in predictable steps. If we track the combined score of all substrings ending at our current element using a single running variable, we can calculate the next position's score using an incremental jump. This is dynamic programming. Store one table entry for each ending index. But what happens if the new character isn't unique? This is the core breakthrough. When we encounter a repeating character, like this second letter, it already exists in any substring that extends back past its last recorded position at index 0. Therefore, those older substrings gain 0 new unique letters. Only the newer substrings starting after that boundary get a score bump of +1. Mathematically, the number of substrings that actually benefit from our new letter is exactly equal to the distance between our current index I and the character's previous location. By tracking the last seen position of all 26 English letters, we can compute this score step in constant time. By combining these pieces, our strategy becomes beautifully simple. We make a single pass through our string. At each letter, we calculate the incremental change to our current contribution, add it to our running total, and update our tracking map. This converts an intractable cubic problem into a highly optimized, linear time masterpiece. To implement this solution, we allocate an array dp of the same length as our string to store the contribution at each step. We also prepare a lookup map initialized to -1 to track the last seen index of each character, and a grand total counter set to 0. At index 0, we encounter the letter A. Since we haven't seen A before, its last seen value is -1. Plugging this into our formula gives us 0 plus 0 minus -1, which evaluates to 1. We save this in dp0, add it to our grand total, and log index 0 for A. We continue our linear march forward. For the letter B at index 1, its contribution is the previous score of 1 plus its distance of 2, which equals 3. For the letter C at index 2, its contribution expands to 3 plus 3, which equals 6. Our running total sums up to 10. Finally, at index 3, we encounter the letter A again. Our lookup map shows we last saw letter A at index 0. This time, instead of gaining a full boundary jump, the contribution is capped at the previous score of 6 plus the distance of 3 minus 0. This gives us 9, bringing our final aggregate total appeal to 19. While this array method works flawlessly, notice a massive optimization opportunity. As we marched forward, our formula only ever looked back at the immediately preceding cell to compute the next value. We don't need a whole array. We can drop the array entirely. By replacing our array with a single rolling integer variable, we can update our contribution value in place at every step and add it immediately straight to our running sum. This drops our auxiliary storage space down to true constant memory. N is the length of S, time is O of n. We scan the string once and do constant work at each index to update the rolling contribution, the total, and the last seen map. Space is O of 1, current contribution, total sum, and last seen for 26 letters. A full DP array with one entry per index would use O of n space instead. Function appeal sum takes the string S. Initialize last seen so every letter maps to -1. Start current contribution and total sum at 0. Loop index I across the string from 0 to length -1. Read the character at position I. Extend current contribution by I minus the last index where we saw this character. Add the updated contribution into total sum. Record index I as the new last seen spot for this character. Return total sum as the answer.